The most important thing in this chapter is symmetry. And we look at three forms of symmetry. First one is spherical symmetry. Second one is cylindrical symmetry. And the third one is flat surfaces, flat planes. First, let us consider a case of spherical symmetry. We have a spherical shell of charge. Shell is hollow sphere. Charge is uniformly distributed. That is important because of symmetry. If it is a conductor, charge will automatically get uniformly distributed. And we want to find the electric field at every point inside and every point outside. So we draw a spherical Gaussian surface, symmetrical with this, with the same center. And this is at a distance r. We want to find the electric field at this point P. The same symmetry arguments that we discussed earlier are valid. At every point, electric field will be radially outwards. And at every point, the electric field vector will be parallel to dA vector because dA vector also will be radially outwards. Since this is symmetrical, same distance from this spherical shell, all points will have the same magnitude of electric field. Therefore, this integration E vector dot dA vector over the entire closed surface will simply become E into A. And Gauss law tells us this is equal to Q enclosed by epsilon naught. If the charge on this spherical shell is small q, then E into A is small q by epsilon naught. Therefore, the electric field here will simply become Q by A epsilon naught. Area here is 4 pi r square, the area, surface area of this Gaussian surface. So we'll get 1 by 4 pi epsilon naught Q by r square. That we also know from shell theorem, because this spherical shell can be replaced by a point charge at center for outside points. Now if we consider a Gaussian surface inside this, so now no charge is enclosed here, right? If no charge is enclosed, then the charge enclosed is 0. Okay, so therefore integration of E vector dot dA vector will be equal to 0 by epsilon naught because no charge is enclosed. Symmetry arguments will still hold. Now the E vector will be radially inside, dA vector is radially outwards. So if you do E vector dot dA vector, you'll get E dA cos of 180 degrees, which is minus E dA. Again, E will have the same magnitude. So basically this integration will come out as minus EA equal to 0. So E is equal to 0. At every point inside the spherical shell, electric field is 0. At every point outside, the spherical shell behaves like a point charge at center. This is the same result that we got from shell theorem. Shell theorem also told us the same thing, that if a spherical shell of charge is there, charge uniformly distributed, then for outside points it behaves like a point charge at center, and at every point inside electric field is 0. If we make the ER graph, at every point inside electric field will be 0. As we come to the surface, electric field reaches a maximum value, then it falls off as 1 over r square. Now E inside would not have been 0 if charge was not uniformly distributed. Because this charge is uniformly distributed, if we consider any point inside and we add up the electric field into all the charges, we find that the electric field here at every point inside turns out to be 0. If charge is not uniformly distributed, E inside will not be 0. Gauss law and shell theorem are valid because electric field and hence electric force is proportional to 1 by r square. Because of this inverse square relationship, these laws are valid. So therefore the same laws can be applied to gravitation also.